So why even come to this? Why do I care about whiskers? Are they bad? Should I have a mitigation plan? What kind of information can help me do this? The electronics industry, we deal with a weird part of the elemental table. Don't ask me why, we latched on to lead and tin and some other things. Tin is one of these really screwy elements. It's one of the ancient materials. It's been around for thousands of years. Civilizations use it for a lot of things. If you take a bar of pure tin and you bend it real quickly, it cries. It makes an audible noise. There's only two other elements that do that. So it's kind of an odd thing for one of the elements to do. One thing I learned in school, and I've actually got to go to a couple plants, the way that a lot of glass is made is on a molten bed of tin. Gets it nice and flat and uniform. Getting that glass off is kind of crazy, but they do that. Tin forms something called tin pest, tin plague. There's about 11 elements that have two different crystal structures. It's called allotropism. Really weird because sometimes it's in like a body-centered versus a face-centered. It changes depending on temperature and a couple other things. Tin is one of those. Tin, because it does it at minus 13 degrees C, human civilization's seen that. Tin pest, plague, comes from the German word that a lot of times in Germany in really cold winters, their organ pipes were made out of tin. And if it got cold enough and if the tin was pure enough, they'd come in and they'd look like a bug had infested it. They had a plague on it. It would just slowly turn to dust. When tin changes its crystal structure, it changes volume by 27%. And when it increases, it just turns to powder. There is one famous incident that's recorded. They had a whole bunch of tin bar going to St. Petersburg in Russia. Forget the year, but they had a horrible winter. When the train left wherever it was in Europe, it was full of tin bar. When it got to St. Petersburg and went through the cold, it was full of powder. And of course, they had no clue what happened. It was to them a big mystery why all this changed. Well, the tin had just turned into tin pest and grew in volume and turned into powder. Of course, the last thing is tin will form whiskers. Tin isn't the only thing that forms whiskers, but for most of us, it is the biggie. Cadmium and zinc also do that. Zinc, we see a lot of zinc whiskers. I've got a neat chunk of data later on in the presentation. A lot of zinc plating on the bottom of the floors in computer rooms, where they've got an elevated floor in the back and that's a zincated sheet, and those are turning whiskers. The whiskers fall off, get pulled into the ventilation system of the room, and then get scattered all over the electronics and start to short everything out. And people are like, I don't understand what's happening. Well, if you look at it, you can find the whiskers. Why do we even care about? Yeah, shoot.
My boss is all keen about silver whiskers as well. I know it's a different mechanism. Is there a body of knowledge around that?
Silver doesn't whisker, and later on I'll show you. Silver, and that's one of the neat things. By training, I'm a material engineer, I'm a metallurgist. We have done the industry a huge disservice. When we see something, oh, it's a whisker. Well, it's a crystal structure. A whisker is a very specific crystal structure. Who has seen electrochemical dendrites on boards? They got corrosion, dendrites.
Yeah.
Dendrites are a structure. Intermetallic needles, I'll show you some other things. Those are a structure. A whisker is a real specific form. Silver will form dendrites, it'll form crystal structures, but it doesn't whisker. But if you look at the literature, you'll see, oh yeah, we had silver whiskers. Well, they had silver crystalline structures, but they weren't whiskers. And I'll get into that, so make sure I cover that as I get down there. I've got a couple examples. In fact, I've got a good one of silver dendrites I should have put in. But I've got some other stuff. So yeah, silver has a lot of crystal problems. Silver sulfide, silver chloride, and you'll see those forms, but it isn't a whisker. It can cause some of the same things, but they're not self-propagating. So remind me, we'll go through some of that too.
Yeah, okay.
Why do we even care about this? The way I like to explain it is some kids were chewing on circuit boards in Europe, and so they thought that was a bad idea, and so now we need the Wee and Ross legislation. WE stands for waste from electrical and electronic equipment, and its focus is on recycling. And one of the real interesting things as this came about back in 2003 through 2006 is that RoHS was actually first put out by the Green parties in Europe, and it got very little traction. They looked at it, and a lot of people said, that's just, you're pushing, and that's on your agenda. And then they added, they actually started with this, and then they said, well, it's part of a recycling thing. then the general public goes, oh, recycling's good, we like that. And so I thought this was gonna die until this got attached to it. And now we have Ross, and Ross 2 came out. Ross 1, restriction of certain hazardous substances, came out in 2006. It banned these materials: lead, mercury, cadmium, hexchrome, and the 2 fire retardants, which, since I'm a metallurgist and not an organic guy, I had never tried to say these because I always mess them up. A lot of us in electronics don't have these. They're in our chairs, they're in the carpet, they're a fire retardant. We have other fire retardants that we use as part of our industry. It wasn't really these. Actually, when Rockwell went through, we started looking as this came about. We only had 1 circuit board that was being used kind of as a stabilizer on a heads-up display unit, and it had, I think, the second one in it. And so we just substituted for some FR4. It's simple to do. Mercury, most of the planets understood mercury for a long time. We've got a lot of mercury out of the way. There are still mercury switches. You know, the thing I like about the periodic table is, you know, it's finite. It isn't going away. You can say we're not going to use something on there, but you have to have a substitute. The new light bulbs, they have a little bit of mercury in them, yet that's what we're all going to. So mercury has its place, but most of the mercury uses that we had in the industry have gone away. We've substituted out. There's still a few things. CAD and salt water. I was in the salt water on Tuesday on Manly Bay. There's a lot of salt water out there. And cadmium connectors and salt water is the best thing. If you substitute stainless steel or zinc, cadmium is king. So there are exemptions that we can still use CAD in some of our electronics. Where they really push back is screws and nuts, some of the hardware. And in many cases, you can go to nickel or stainless steel and a lot of that and still be okay. Hexchrome was one of the things we see on a lot of aluminum chassis. There are some substitutes. They aren't as good. I'm really interested to see where the industry is going to finally settle out. A lot of the hexchrome use I know on aluminum chassis, the engineers did it because the engineering team before them used it. They just grandfathered it along. They never really looked and said, "Do I really need this?" A lot of times you find it on chassis just to make sure I can pass some salt fog testing. Well, a lot of times they didn't test it without it. Of course, testing costs money, and they're trying to make sure they pass the test the first time. So a lot of our hex chrome uses aren't necessarily things we need, and the industry is kind of going through understanding it. The biggie is lead. 37% of every solder joint you made had lead in it. And so changing and getting rid of the lead is what's really, really painful. This went into place 2006. Most of us kind of said, oh, great, away we go. A lot of the industry, if you're making military or national security, if you were making airplanes or things along those lines, a lot of transportation, we were either had an exemption or we were excluded. We weren't part of the scope. And this was called a closed scope. And after a few years of doing this, the Green Party looked at Rojas 1 and said, funny, no one's being written up for this. No one's being fined. No one's being, things don't seem to change. They went out and sampled product. 40% of the product coming in Europe still had lead in it, when it shouldn't have. It should have been in products. And so they said, oh, the legislation isn't tight enough, so we'll change it around. So it just passed the 2011, late 2010, Rojas 2 went into effect. And what they did is they changed the scope. It used to be under Rojas 1, if you were mentioned, you had to worry about it. If you weren't mentioned, you were fine. You were outside of scope. This is open scope. If you don't have a listed exemption in the legislation, you're under the rules. And so they flipped it around 180 degrees. Well, it makes a whole lot more products get tucked into it. One of the good things that, at least from my standpoint for Rockwell Collins, is they actually put a transportation exemption in there. Automobiles, anything that moves people has a stated exemption. So for avionics, we're in good shape. The problem is we all use the same global supply base. And so, I might buy 1,000 parts from Rotorola. They don't care if I'm buying 1,000 parts. They care about the people who are buying 1,000,000 parts. So the supply base decided we're going to meet Rojas. That meant all my suppliers changed. So suddenly I have to deal with pure tin parts coming in. I have to deal with those parts of things. No one had an idea, even imagined it would have that big of impact. No one considered that the supply base was the thing to be concerned about, not us making our product. The stuff we make our products with had the biggest impact. We're going to talk a lot about that today. I found some really goofy history stuff, which I think is kind of cool, rose into. Some of us remember back in '73 when 8-track tapes were the rage and they were cool, and we'll never get rid of 8-track tapes. And then, before 8-tracks, we're still using vinyl records. I have to talk to my co-ops and say, yeah, a record, an LP, what's that? Think of a CD that's black and really big. They just never seen them. That generation doesn't understand them. They still look at this chart and kind of wonder, well, what replaced all this? Cassette tapes. And so back in the early 90s, it hit its peak. Well, again, technology keeps moving. What replaces that? CDs. And now 2009, I should go out and see if I can get this updated, now digital has gone away. So technology is always evolving. And if we don't evolve with it, we're going to have some problems. That's the reason I throw this up. If you look back in Q1 of 2005, and this was from, you'll notice all throughout today, I try to put my sources down here so you can go out on the web and pull these up, especially if you're using someone's paper, things like that. So if you have trouble getting to this stuff, send me an email. I should have it in my file someplace, and I'll try to send it to you. Q1 2005, if you look at what the world consumption of tin lead solder versus lead-free solder, back right before Rojas 1 went into effect, we're about 73% tin lead, 27% lead-free. And again, we've been using lead-free solder for a long time. It just wasn't the driver, it wasn't the dominant. Rojas goes into effect, and the world starts to evolve. So you look at Q4, the beginning of last year, it's completely reversed itself. I always say 70-30 because it's easier to do, but now we're 70-30. Most of the world has gone to lead-free. Things aren't falling apart. Lead-free does work. Who's building with lead-free right now? Okay, I have just a little bit. I'm just learning. We've got 3 products, so for me it's been sometimes a painful learning curve. I don't always get it, and we found out, experience is what you get right after you need it. We've done it that way. But this 30% down here, a lot of that is the high performance, life critical, flight critical type of things. This will keep falling. I really believe I'm going to watch this table. But you notice we're starting to plateau out now. Now we're starting to flatten out. Again, either a change in legislation, or as we understand things better, we'll start to move into that. But it is here. I have a lot of friends that say, oh, we should go back to tin lead. I look at that graph and say, sure. What tells you that this is going to reverse? It isn't. Lead-free is here to stay, and we just have to adapt to it.
Dave,
Sure.
we talked about how component suppliers are what changed. I'm still a little unsure, what in a component that's not soldered to a board yet, where's the lead?
Some of the lead, as far as maybe down in here, die attach is one place where they haven't found a substitute high lead for attaching the die in packages. In fact, a year and a half ago, EEVblog, the legislation that governs automobiles that comes out of Europe, they went through and did a revision of that legislation. And they told the automotive guys, well, you're going to lose your exemption for high lead die attach, which I just sat back and laughed, because then you can see this disconnect between the people that are trying to put together legislation and the technical community. Because I've got a buddy, Rich Parker, at Delphi, and Rich just laughed. He said, cool, they don't need electronics in their cars. They'll be okay. They'll get along just fine without them. There is no substitute. They're looking very hard. They want to meet the legislation. They understand the drive, but it's not there. So yeah, if it isn't just lead on the leads, sometimes it's down inside the parts. If you think of a piezoelectric crystal, part of that material is lead. That's why it works. So now they have found a substitute. They still have some exemptions, but within Rojas 2, they made it a lot stricter for how long these exemptions are going to go on. What I'd like to see, what a lot of the industry has asked for, and I don't know if it's going to happen, is we have REACH and we have Rojas. REACH just bans everything, or I'm sorry, Rojas just flat out bans it, says it goes away. REACH, at least to me as an engineer, I have a whole process. Why I want to use it, how long I want to use it. I can turn in a dossier with documentation on why I need to keep it. Rojas has none of those mechanics. The problem is REACH and Rojas are done by 2 different groups in the legislation. And of course, no one wants to be retired and have their legislation go away. I'm hoping industry has a lot of input to that. And eventually, I think we'll get to where we're all doing something with REACH, not Rojas. We'll wait and see. But yeah, lead shows up in lots of weird little places. Who's familiar with electroless nickel immersion gold, EEVblog board finishes? They put like 1,100 parts per million or billion in the plating bath as a stabilizer. I didn't know it, but that's over the limit, so they've had to go in and revise our baths. So it shows up in a lot of just little places you'd never think. In the US, I don't know if it was here in Australia, we used to have lead and gas. Stupid. Didn't need lead and gas. No wonder we're putting lead all over the planet. I'm an avid waterfowler. I shoot as many ducks as will actually fly into my shot pattern because I can't hit the broadside of the barn some days. In the US and North America, they did a huge study that showed 9% of the fatalities on the flyway were the ducks picking up stray lead pellets in the swamps because they're just too shallow and they could get to it. We got rid of lead shot. It cost money, it took time. I have better ballistics now than I ever had. You know, I used to pay $8 for a box of shells. Now I'm paying $12, but the data said it's time to change. So sometimes it takes legislation to really highlight where is all this element being used and do you really need it. We kind of work with our pocketbooks, not so much with common sense some days, but it's a push. Some of what's going on is not good science, but we as engineers have to deal with it and go forward. And I think we can get there. We're gonna have to be better engineers to do it. It's not as simple as a material system as tin lead, and we'll talk about that today. Here's your components. Here's where they're coming from. And this is actually old data I got from Cal, so I need to update this, but 55% of everything you're getting exposed to is typically a pure tin. When I say pure tin, I mean 97% tin or better. So if it's got 3% of something in it, that's what the industry adopted as a definition. There's also what Mike Osterman found from Cal, so 4% of this has tin of some concentration, they just don't know what. So if you add, 60% of this graph potentially could whisker. So 60% of your parts coming in. What I get a kick out of it is everyone says they confuse lead-free soldering and whiskers. We've had lead-free components, lead-free soldering for years. Gold is lead-free. So why are you worried about lead-free parts? We're worried about pure tin parts. And you're gonna have to talk to your customers because the customer base still doesn't understand there's a difference between lead-free and pure tin. And you can bring in a lot of pure tin, nickel, palladium, gold, palladium, silver. You have a lot of finishes we have historically used. They're RoHS compliant, they're lead-free, but they're not a tin whisker risk. And a lot of times I've had long discussion with customers on that. So that's the background. I think what we'll do is we'll dive in here and we'll talk a little bit about, we could spend hours on basics. I'm just gonna give you some of the biggies up front, run through those so that we're all on the same baseline. Again, pure tin, the industry definition, what's been adopted is that if it's 97% or better, that's pure tin. 3% of anything, bismuth, gold, you name it. Put 3% in here and you're okay. Propensity, you're gonna hear me say it a few times. If you have tin, you can whisker. If you don't want whiskers, don't have tin. It's that simple. If you have a tin surface, there is a natural tendency for it to relieve its stress by growing a whisker. Whiskers tend to be single crystals, just like the turbine blades we have in jet engines. What tin is doing is growing a single crystal, though there have been some cases of some multi-crystals being shown. They tend to be the exception, not the rule. Mitigation doesn't mean that you're going to eliminate it. It just means you're going to deal with it, lessen it, control it. Doesn't mean eliminate. I've had with a couple customers, oh, you're going to mitigate it so I won't have tin whiskers. No. Mitigation means I'm going to try to keep the risk low. No different than having a solder joint crack, no different than having corrosion on the board. It's just another failure mechanism we're dealing with. They do grow spontaneously, and I'll show you a really neat example of that in here. Sometimes you see whiskers grow right away, and that's what they tend to do. They tend to, if you're going to have a whisker problem, you see it. But there's a number of very good documented cases where something has been sitting there for 3 years and suddenly it grows a whisker. And that's the problem we have as engineers. We can deal with stuff that we can test, look at, categorize, but when you have this unknown time frame, especially my safety and reliability guys, will give me the MTBF of whisker growing. Good luck with that. I can't even calculate it. No one has that number. And then you're gonna hear me talk about commercial off the shelf. The things you control are fine, but commercial off the shelf or COTS, when you're buying stuff from your suppliers, that's COTS material, what are they doing for tin whisker risk? Sometimes your biggest risk whisker risk, what your most exposure is, isn't the stuff you're doing in-house. It's buying a subassembly from somebody, understanding what they did and how they put things together.
Dave, is there any particular percentage at which the Tin Whiskers no longer form? So if you're having tin lead,
Yes and no. I'll get to part of that. In fact, I think, yeah, that's coming up. There's a couple things. In general, whiskers are, and there's a lot of data that give you a nice bell curve. What's the typical length of whisker? And based on that, a lot of the models and things you're going to see today, we've created risk factors. Okay, a typical whisker has a diameter of X, Y, and it's so long. And we put that in there. But I'll show you some. And what people focus on is these huge gargantuan whiskers. And that's what your customers unfortunately go, well, you have a whisker that spanned 2 inches. Yeah, and the probability of having that whisker is like 1 in 2 zillion. You should be worrying about the whisker that's a 1/4 inch long, not 2 inches long. And so I've got a little bit of that data tucked in here. What I think is what I put in, the thing I get a kick out of, we've known about whiskers since 1951. We actually had whisker problems on hardware, some of the first electronics in World War II. The guys at Bell Lab took a look at it and said, I know what's going on here. The tin's relieving stress, it's making a single crystal, it's growing. This is out of Compton's work. He had whiskers growing on things. Pure tin was easy for them to plate back then. The baths were very rudimentary, just real basic. They also saw it on zinc and cad. They took a look at it. They said, if you put a little bit of lead in here, it goes away. And oh, by the way, if you use tin lead and you use the eutectic alloy at 183 degrees C, it goes from a liquid to a solid at one temperature, 1 point, like a light switch. You're good, don't worry about it. So we bumbled along for the last 60, 70 years until Rojas came in. We had the technical solution. It's been taken away, so now we have to adjust. And why tin? Why, when Rojas came back up, why go back to tin? Well, tin's solderable, it's cheap, it's easy to control. The problem is not all baths are created equal. And I'll talk more to that as we go through some of the cells. But just because one supplier has a bath and shown you some stuff, doesn't mean the next chemical supplier, that bath will act the same. And that's a problem that we have to deal with as assemblers. A couple things that are industry consensus. Bright tin and matte tin. You'll never see a clean definition. The GEIA standard 0005-2 used to try to have a definition of what was bright and what was matte, took it out. There's just no standard. Nobody in the industry can agree on it. But we do know that bright tin whiskers like chia pet. So if you don't want whiskers, make sure you're not using bright tin. Another engineer and I have been going through our Rockwell stuff for the last 5 years, and last week a chassis showed up. That has bright tin on it. Okay, time to get rid of it. It was something that they put in place back in 1967. It's been working ever since. We did a lot of looking. Do we have whiskers? Didn't see any, but bright tin will whisker no matter what, and so that's one of the givens. Part of the reason is bright tin is bright because they co-deposit a whole lot of organics out of the bath. That's what makes it look so nice. Well, those co-deposit organics also push the stress level up in the tin through the roof. And stress in the tin plating, that's why we have whiskers. That's the number one thing that the industry has agreed upon. So you need to get away from bright tin. If you're in matte tin, you're better off. But again, we don't know what that definition varies from plater to plater. If you put a nickel barrier over, typically you have a copper lead, you're gonna put a nickel barrier down there. Nickel and how you control the intermetallic between the tin plating and whatever metallurgy is below it, that helps a lot. And tin and nickel form a very laminar, very smooth intermetallic, and I'll talk more to that, but being able to look at the influence of what having a barrier layer does will help you out in some cases. The lead frame, alloy 42. Alloy 42 was used, it's gone away, thank goodness, in a lot of packages because it has a CTE of about 6 or 7, and a lot of the die and lead frames and glass around where the alloy 42 is used has a CTE about 6 or 7. So it means it's matched and makes a really nice component. The problem is, at least what my mentors have taught me, if the stress isn't coming, so I don't have a stressed lead, but that stress has to go somewhere. It just doesn't go to 0. So where does it go? It goes into the finish. So if you look at a lot of the studies, lots of us use alloy 42 because there's so much stress being put into the finish or put into the solder joint that it automatically whiskers. A lot of people won't use alloy 42 parts because it puts a lot more stress into the solder joints. In fact, alloy 42 T-stops, we don't use at Collins. I can show you they'll crack in 30% faster than if it was a copper lead. Now, it's got to be a big part. Most of us are using SOT 23s. They all use alloy 42. SOT 8, SOT 6. But when you start getting bigger, depending on what your product and use environment, that gets to be a problem.
How big we have to worry about? How big is big for it to worry about?
As a rough rule of thumb, anything that's a SOT 6 and a SOT 8, you know, SOC 6, smaller than that, I haven't seen a lot of issues. Part of that could be because those parts are so small. When we solder them, we're just automatically putting lead in places. But like I've seen, and they're not very prominent, but like a quad flat pack, there are still some big, tall quad flat packs that use alloy 42. And I've seen whiskers at the top where the solder wasn't. I've seen whiskers coming off those. So anything that's multiple leads, I'd say greater than 10, you know, I would take a look and wonder and see what you're doing.
But what you were just saying is the small ones, the lead will come up. But if you're doing lead for a solder, you won't get that advantage.
Won't get that, but you get another effect, and I will cover that later today. You bet. We trade poisoning in tin lead for melting in lead-free, and I've got a really cool data set I can show you guys. In fact, it's what I had that discussion with the customer 3 weeks ago on my 3 assemblies, because he wanted to know, well, okay, I'm not using lead as poisoning anymore. What am I going to do? I said, let me show you a couple charts, and I've got those in here. The one thing that's popped up, which I think is real interesting, is as an industry we've been being beat over the head. Worry about your parts, worry about your parts, worry about your parts. Well, where do we keep seeing the whiskers? Hardware. This is a bracket on an old 1970s design, and you see the whisker? This is a bright acid plated bracket, and so it's growing little whiskers. This whisker grew all the way up in contact to that and shorted it out. And I've got a better picture I'll show later. This is the famous NASA card guide, where they opened up the NASA flight computers, and they had all these whiskers growing on here. And NASA looked at them, I loved it, and they said, okay, we're just going to brush them off and vacuum everything up and we'll be okay. And that's what they did. And the last 3 or 4 flights had these units in, they flew just fine. So, you know, mitigation, you can justify a lot of things, but the hardware, a couple of years, the guys from Delphi at an IPC meeting got up, and they showed they've been going lead-free for a long time, just getting ready for things. And they said their number one problem, if they're going to have a whisker problem, is not components. It's hardware, shields, brackets. Think of the little things you buy. And part of that is we buy them from the cheapest vendor I can get, who's not probably controlling his bath very well. It's just part of our nature where we're buying some of the stuff and how it's procured. It doesn't have a lot of, you know, it wouldn't be a 10-cent shield if I had all the documentation and everything else tied to it. So you get what you pay for. And you'll see as we go through the presentation today, I got a whole lot more things. Most of it is wrapped around when you see big whisker problems. It's hardware type of things. Tin whiskers are not electromigration. Everyone has seen where you get a dendrite growing. Whiskers don't need a bias, they don't need moisture, and they don't need electrolyte. And to get electrochemical migration, to grow dendrites, you need those 3 things to make a battery. We do not get those with tin whiskers. Tin whiskers can just grow. I said it before, I'll say it all day, if you have tin, you can whisker. In fact, I plan on at some point it's going to whisker, and I'm going to mitigate around that. If you have tin, the chances of it will never whisker are very low. Tin, as an element, that's part of what it does. Zinc is the same way, cad's the same way. As a material engineer, I think it's easier to deal with that than look at it from, well, it might, no, it's going to whisker and I should mitigate it. It's a diffusion thing. Early on, when we got back into whiskers, if you look back at the historical record, the guys at Bell Labs say, oh yeah, these grow from the bottom. And so people are looking at this trying to think, well, if it's growing from down here, all the material is growing here, this whisker is coming out of the surface, shouldn't there be a hole? All those atoms had to come from somewhere. And Dr. Tom Woodrow did some work out of Boeing, and he shows that the atoms that add on and make up the bulk of a whisker come from a huge area. That's why we don't have nice little holes and wells and voids of where things have been depleted. It's diffusion on a very large scale, which is one of the problems. That means whiskers can grow. You can't just treat a little spot. You have to treat the whole thing to deal with tin whiskers. It is industry consensus that it is stress in the plating. And the reason the tin grows a whisker is to relieve stress. And other metal systems do that. Tin, lead, gold, a lot of them do. Unfortunately, because tin recrystallizes at room temperature, it's primed to say, okay, I'm going to get rid of stress right now. And what's it do? Okay, I'll grow a whisker. It's just common mechanism. The growth rate on these is pretty variable. You can see them grow like crazy, or sometimes they'll grow and stop. Sometimes they'll just grow and never grow again. Sometimes they'll grow, stop, and grow farther 5 years later. Again, that's part of the problem. As engineers, we don't have a nice prediction. There's no formula to say, okay, I know it's going to grow at this certain rate, therefore I can use that as part of my mitigation strategy. Just, it's not documented, it's not understood well enough. Here is some of the stuff I have seen thrown up on why we have whiskers. This is the number one. This is what the whole industry, if you talk to a lot of people, will all agree. They may say, instead of compressive, some tensile stress, though that usually doesn't make a lot of sense, but I've seen several cases and a couple of my own where a section's under tensile stress, not compressive, and I'm still growing whiskers. We as an industry really don't quite understand these. A part of it is what makes a whisker grow is a multi-factored equation. It isn't just one or two variables. It takes several things, and of course when we get equations like that, and we don't control the whole process, it's very hard to predict what's going to happen. I'll show you some cases where they talk about the intermetallic compounds between the tin and the copper that it's on, that those intermetallics can cause stress and grow whiskers. The deposit thickness. Thin coatings tend to whisker more than thick coatings. And part of that is how stressed the coating is. And that's something I'm going to talk about we can use a little bit. What's my substrate? If I'm on alloy 42 or ceramic, that's a whole lot worse than being on copper. You know, it just depends on what that substrate is giving an influence. It's putting stress, it's adding to the stress of the finish, and that will help influence what's going on. This has been mentioned a few times. I haven't seen anyone chase it, but incorporated hydrogen. Hydrogen can, in plating, we know that hydrogen embrittlement in steels, hydrogen embrittlement in chrome plating causes issues. And there's been 2 or 3 papers out in the industry that think that at least it hasn't been discounted and it hasn't really been shown as a major driver, but I put it up here just so you have the information. You know, could hydrogen in the plating be causing some of the stress or causing some of the reactions? And people are still looking at that. A lot of work on grain size, structure, and orientation, and we'll talk about that. I downplay this part of it mainly because I can't control it. What I get is what I get. I mean, I could tell a vendor, I want all the grains orientated in a 1-1-1 direction. And they just look at you and smile and say, sure you do. They don't have control of it. So it is neat to know this stuff. It tells us a lot about what's going on, but in terms of what it buys us, I don't see it as a big helper. Again, co-deposited carbon and organics, bright acid tin, big no-no. And then some alloying elements, they found like if you have aluminum and a couple other things, you can actually make whiskers grow faster. Most of these things we don't have in our system, but it's part of the data that's out there and part of the research.
So what was it, you didn't say, you didn't have most of those in your system, your alloy?
Like aluminum. You don't find aluminum, you know, academically they put like a few parts per million aluminum in a tin plating, and it grows whiskers faster. But we normally, your vendors wouldn't be delivering something like that to you. I think magnesium is one of the others that some of the academic work has shown, because you know, they did what they usually do. Okay, I have tin, let's put a lot of elements in and see which elements try to drive more whisker growth or less whisker growth. Luckily, the things that drive whisker growth, at least what they've shown, like aluminum and magnesium, we don't have in our system. They're not delivered to us that way. If they did, we'd really be in trouble. I don't know what I'd tell them. Okay, please, no more aluminum. Electrically, these things can carry some current, and I've got another cell on just a data point I've seen them out in the literature. They are resistive to a point, and I actually have some metal vapor arc where I can show you how they go poof and blow up and burn. One of the nice things is a tin whisker has a tin oxide on the outside of it, just like a tin surface. Tin oxide is a non-conductor. Okay, so if that whisker just leans up against a surface, the oxide's working for us. If that whisker's rubbing and it can break the oxide down, now the tin metal inside on the whisker might be able to make contact. So we get a little bit of benefit from just standard metallurgy, having an oxide that doesn't conduct. You know, a lot of times you see whiskers just laying on things. That's not going to take it. It's got to do some impingement. It's got to be trying to make a connection. It also is one of the things where things, you know, sometimes they'll just burn out and go away, just like dendrites. You see some no-fault founds on equipment. Well, a dendrite grew, it got enough current, it blew it out, and now it's back to normal. You just don't see it. Some of that behavior we see with whiskers. And then there's a bunch of things that we need to worry about design. This is type of the material side of it. This is the design side of it. This is this is really what we control.
Well,
What's your...
Sorry, why you mentioned voltage bias there? Because earlier you said that, early on you said it's not electromigration, so therefore not related to voltage.
Voltage bias, and there's 2 papers out there that if you apply a voltage, the whiskers bend toward it. Which is like, and I don't know what to do with that one. I try to make sure I've got everything. There's 2 papers, and they're really good solid papers, and then say, yeah, the whiskers will bend over. Well, do you mean to say that if I got the circuit here and it has a certain bias, it's gonna try to, you know, electrically attract it? So I look at this as what kind of voltage am I putting through? You know, if I have a lot of voltage, I might get really worried. And you'll see when we get into metal vapor arc, lower voltages I think are a safe place to be. So in a lot of our circuits, we start out 5 volts, and then 3, and then I think it's 1 is what the design team told me. You know, we're going down in voltage, and that's a good place to go. We're also getting smaller, which is a bad place to go because the closer things are together, the more chance I can bridge. So we've got 2 things kind of working against us. Redundancy. This finally went into the GEIA spec, and we pushed real hard and we said, you know, if I'm mitigating and I have redundant circuits in there, if one bridges, why isn't redundancy counts for part of my mitigation? Then the standard didn't do that before. And a lot of customers, I mean, a lot of our designs, we have redundancy built into them. Not for whiskers, because there might be a short, there might be corrosion, something might happen. Well, for all those other failure mechanisms, redundancy was a valid mitigation. So why wouldn't redundancy be a valid mitigation for a whisker? It is. Part of the industry wouldn't accept it for a long time. I didn't understand that. And I looked at it and said, that just doesn't, that's not good standard engineering. So this has started to change. People are starting to look at this and say, if I have redundancy in the equipment and it deals with other types of defects, then whiskers is no different. It should fall under the same protocol. And so we're in pretty good shape, I think, with that. You know, do you have critical circuits? If you have critical circuits, critical components, maybe those shouldn't be in pure tin. Maybe those should be in another surface finish. Maybe you need to do something. So from a design standpoint, if you're worried about whiskers, you know, what's the critical parts of the system that I need to focus on? And then coatings. We're going to spend a bunch of time. Solder mask, conformal coat, or if you just encapsulate or pot a unit, those don't stop a whisker. They separate them, they capture them, they keep them away from things. And this is one of the main things, conformal coat. You're going to hear me say post coat because at Rockwell, it's the thing we do after in the post operations. So our slang is post coat, but I try to use conformal coat. Conformal coat is to me, it's our savior. It's the one thing I can control and use, and I can really show my customer that I can deal with conformal coat. Now, who doesn't use conformal coat? Anybody in the room? That gets to be a problem. We have some RF stuff, and the guys go, well, you telling me conformal coat's #1? Yeah, and I'll use conformal coat. Okay.
Well, that's interesting because I noticed I had a quick look through your slides before I came in, and you haven't referenced an industry body called INEMI.
Yep.
And I know they brought out a paper that they did a lot of research, and once they said they reckon conformal coating was still an unknown area. That was a couple of years ago, and weren't keen to recommend it as a real mitigation. That's my understanding.
And your understanding is right. I think we've moved more toward it is, but there's a couple things I'm going to highlight that we have been using conformal coat. Oh, it's a mitigator? Wait a second. Got to think about this for a minute. So some of what INEMI, I don't always agree with the INEMI studies. They do some outstanding work. They have done some of the baseline studies. If they hadn't done it, we wouldn't know certain things. But a lot of the INEMI stuff, now we've got some more data, and I'll show you as part of that.
And they don't seem to have done much most of the time. They seem to go in other directions.
A little bit. I'll show you a couple other things that where people have gone in and looked at. Our problem with conformal coating is we've been conformal coating to take care of environmental, okay?
Humidity and things like that.
Water, dust, dirt.
That's right.
If we don't change any of that around, is it still applicable whiskers? Not really, not without some stuff. And I'll show you why. There's a couple studies. There's a big industry study about to happen to look at that, because if we're going to claim conformal coat is a mitigator, conformal coat, the way we have been doing it, it needs to be reviewed and demonstrated, and you need to have a data set to present to your customer why conformal coat, the way you do it, works. Now, and I'll show some of that. That's big.
You just made me realise that we have two separate classes of boards, DC and RF, and we don't conformal coat the RF.
And neither do I.
Yeah.
And my design teams are just pulling their hair out.
At 50 gig, it's a problem.
Oh yeah?
Yeah. Would selective conformal coating of,
You beat me to it. That's what they do. There's a, I can think of one specific RF design. They have a processor. It comes in pure tin. They can't substitute, so what do? They conformal coat the part, not the whole board. Because if they did the whole board, suddenly, because signal's running up on the surface, a standard conformal coat won't help me. You also see, and I think I touch on it in here, there's a new class of conformal coatings coming out. Some of them are vapor deposit, a lot like Parylene, but different formulations. There's also things like Rockwell Collins working on a liquid glass, where they're angstroms thick. And those have great promise because the RF doesn't care of a coating that's an angstrom thick. You put it 2 or 3 mils thick, okay, now RF and microwave can't stand it. The designs just don't work. So we've got to find that in-between materials that'll work in those cases. And I should cover part of that. Good questions. Keep them coming, gang. I like that. This I threw up, the #1 best site on the planet, NASA Goddard. If you put in Tin Whiskers in Google, it will be the first thing that comes up. You can just say NASA Goddard. They have Jay Busey, and I've got a lot of Jays, and Dr. Henning Leinecker. They have some great data. For every case study and story they have on their website, Jay has told me there's 5 they can't talk about. Someone has come to them because they're experts, and can you help us with this? But we can't disclose it. Okay, and they'll do the work to help them, but they can't let it out in the public domain. So for every story you see out here, but they have a huge catalog of pictures and reports and different equipment. And I use this a lot when I'm talking with customers and doing research. And you notice industry consortium, the CALS Consortium, Baltimore, Maryland, INEMI, you mentioned, done a huge amount of work, very instrumental. SMTA and PERM, which is Lead-Free Electronics Risk Mitigation. It's an industry consortia that produced the GEIA specifications that are out there. JEDEC, IPC, and GEIA are also doing a few things, but I would start here. I've got a Tin Whisker question, you're always free to email me, and I may send you off to another colleague in the industry, but what the guys do at NASA Goddard, it's a really good site, really good stuff there. Here's where we're going to. I'm going to start at the bottom, not at the top. The industry data has reported that a whisker can carry from 25 to 50 milliamps and 1 amp for a short time. I'm not a double E. I don't speak Sparky very well, but my double E buddies say that's a problem. That's pretty good. In some circuits, that's an issue, and not good. And typically 10 millimeters. I've seen them a lot longer, a lot shorter, but a lot of the data centers around, they can be as long as 10 millimeters. I know that's a problem. I can see that looking at my circuitry and stuff. The diameter is pretty consistent. They're all between 1 and 3. They don't really get much bigger than that. That's one of the few constants if you look at how a whisker grows. Again, they're single crystal. And after they grow so long, I think it's a 17-degree angle. But there's a specific angle a lot of them bend to. And it's part of their crystallography as they grow. So, but they grow right out of the base. They don't grow by adding atoms up here. And they grow from grabbing tin atoms throughout this whole area. And I've got a video later on you'll get a kick out of. The guys at Brown University, Dr. Eric Chasen, let me have. And you look at it, and they've shot a whisker growing in real time. It's freaky. You look at it and say, no way, it can't happen.